It's a great pleasure to be here, and thank you for getting me over. I think my talk will be a bit different from the others because I'm from the user group. I will tell you what we are doing and what we want, and you can give us suggestions. So as said, I'm from the School of Physics from the University of Western Australia. We are also part of the new Australian Research Council Centre of Excellence for Gravitational Wave Discovery. That's for like 7 years. So before I go on, I should mention that I'm a member of the LIGO Scientific Collaboration, and this is an international collaboration to detect gravitational waves. It consists of more than 50 research institutions and having more than 1,000 members. The small group I have at the UW is called Gravitational Wave Astronomy Group. We have myself and 2 postdocs, and a bundle of students. So our main interest is to detect gravitational waves and the multi-messenger astronomy. That means the electromagnetic radiation associated with gravitational wave sources. But we use high-performance computing. We do supercomputing and do signal processing, and we do machine learning because we want to detect gravitational wave, and we have computational issue. And we also use so-called pulsar timing. That means these fast-spinning neutron stars, they have this pulse arrive at us like a clock. But if there's a gravitational wave present, right, the arrival time of these pulses will be different. So we are also using pulsar timing to detect gravitational wave. That's at different wavelength, though, so I won't be talking about this here. So the outline of my talk is, first I will give an overview, then I'll talk about gravitational wave detection, how do we detect it, and why do we need computing. And then I will introduce our effort at the UWA in terms of fast online detection of gravitational waves. Then I'll give a summary. So what is gravitational wave? The existence of gravitational wave actually was proposed by Einstein's general theory of relativity more than 100 years ago. So the philosophical starting point of Einstein's theory is that the physical laws should be the same everywhere in different reference frame in here or in a moving train, and gravity should not be special. And if you translate this philosophy, basically, philosophical thought into math, you get Einstein's equation, which I won't show. What it says is that what we consider, we should consider the fabric of space and time. We treat time as if it's one of the dimensions, just like the space. So we only consider space and time. And what we found is that the space and time curvature is related to the mass and energy around it. So in a plain language, what it says is that if you have a matter, say the Earth, and if space and time should be flat usually, but if you have matter around it, say Earth there, near the Earth, the space and time curvature should be curved, as shown on here, except this is the space and time fabric, it's not just space. And the second part of the theory says that if the space and time is curved, things will change. It will tell the matter how to move. For instance, near the Earth, here, the light for a faraway observer, light should not travel appear as a straight line. It appear to be curved, the path. So that's actually well tested in experiments. Now, that's about Einstein's theory, but how about gravitational waves? So gravitational waves, also basically predicted by Einstein more than 100 years ago, it's the ripples of the space and time fabric. So it's caused by disturbance of matter. So for instance, just imagine you have a water pond, you have a duck sitting there. Near the duck, the surface of the water is a bit curved, right? But if the duck is moving, it will generate ripples propagating outwards. And that's the wave. And gravitational wave is the same, except it's space and time curvature. It's a bit abstract, but that's just imagine that like the pond. And say you have two black holes moving around and generate disturbance, and you generate these ripples propagating out. Mathematically, it means that the propagation, you have energy and momentum propagate out. And the propagation of this ripple basically follow the wave equation. And Einstein also said the gravitational wave should travel at the speed of light. So fine, there's a theory saying there should be gravitational waves. How do we observe it? So the observational effect is that if there's a gravitational wave, say, going by this way, you have a ring of freely falling object. Remember, now we only consider space and time. There's no such thing about of gravity because it's so combined to the curvature of the space and time. So if you have a ring of freely falling object and gravitational wave goes by, what's going to happen? It's like you are stretching the tire of the bike. You know, stretching this way, it squeezes that way. So it goes stretching and squeezing. Basically, what you find is a change from observer's point of view. It's like the distance is changing, or the light travel time is changing. So the first generation of gravitational wave detector is actually just a single metal bar. We call it the bar detectors. And also, there are many bar detectors in the world, but we also do cryogenic because for low temperature, you reduce the vibration of the bar. And there are 5 in the world. One is at Western Australia, and it's actually sitting at Jinjin, the GDC you were supposed to see. It's called Naobi bar. We got nothing, but because it's only when the gravitational wave frequency is in resonance with the bar, you get the detection, so it's a bit narrow band. So therefore, we have the second generation of gravitational wave detectors, because taking the effect saying here is stretching, there will be squeezing. So we have laser interferometers to combine these two effects. So what you do is, if you're a physics student, you probably will do this kind of experiment on desktop. What you do is that you have a laser shining through here, and that's a beam splitter. Part of the light will be reflected here, and reflected back here. This is a mirror back here and to the sensor. The other part will go through and reflect it back here and come here. So if the gravitational wave is there, you'll cause a phase difference in the two beams of laser coming back. You'll see fringes. So what you detect is the intensity change caused by gravitational waves. As you probably know, we're at the advanced second generation detector, that's laser interferometer already. So there are 3 in operation already. 2 are in the US. That's basically a large, if you know, microsync interferometer basically, and much more sophisticated, of course, with an arm length of 4 kilometers. One is at US, Washington State, the West Coast. One is at Livingston, South Coast. These 2 are about 3,000 kilometers apart. And then one is in the Italy. Actually, it's a French-Italian collaboration. It's 3 kilometers. So what we really measure, if you do the math, what you really measure is the fractional change of the length. It's a dimensionless quantity. So therefore, just by principle, the longer the arm length, the better. So that's what you'll find. Of course, there are 2 more detectors that are under construction. One is LIGO, India. That's actually a copy. There used to be 2 identical copies at Hanford. And the Americans realized that, I realized that because the sky direction of the gravitational wave can be better determined, it's determined by the arrival time, because say you have 2 detectors here. Wave come from this direction, arrive at this detector first, and that detector later. From that information, you get the sky direction. It's like how GPS works, actually. So the longer the baseline, the better. American and Australia will form the longest baseline. That's why in the beginning, actually the Americans gave 1 copy to Australia around 2010. And unfortunately, our Australian government did not accept it, because we need to build tunnels to house it. And Indian immediately took it. So now it's LIGO India. Anyway, so this should be operational in 3 to 5 years. And the other one is in Japan called Kagra. It's a 3 kilometer arm length. It's sort of underground in a tunnel, and it's also cryogenic. So they are going to operate next year. Maybe at less sensitivity, but they are aiming at operating next year. So now we have the detectors. How do we detect gravitational waves, and why is computing important? So here I actually talk about one specific type. There are different types of gravitational waves. Basically, anything with the acceleration of mass quadrupole moment will give you gravitational waves. But the most common one that you probably know about is, we call it binary coalescence of compact objects. That should be two neutron stars when they are very close to each other, or one neutron star, one black hole, or two black holes, stellar mass black holes, like 20 solar mass or 50 solar mass. These are the objects for the ground-based detectors to look for because of the frequency band. And so the waveform we are looking at is sort of this phase is sinusoid. So if for a short time it looked like it's in spiral phase. For this part, if you look at short time, it looks like a sinusoid, but you'll find the amplitude and the frequency increase with time. So what you really detect is so-called chipping signals. And that part of waveform can be calculated using the post-Newtonian expansion. So basically you do Newtonian physics, for instance, and you add general relativity to it to take out energy and momentum from an orbit, for instance. So we actually, theoretically, we know this bit. We can calculate very nicely for this part. And then during the merger, especially for two black holes, you actually have to solve Einstein's equation, and we use numerical simulation to get the waveform, and that took 30 years just to make two black holes orbit each other once. It took us 30 years to get that, but now we are all done. So now we can have a theoretical waveform for the merger phase. Say if you have two black holes merge into each other, in the beginning it's unstable, so there's a rain down phase, and that gravitational wave can also be calculated. And so, and the other thing is that the strength of gravitational wave is really small. Given the length, arm length, 4 kilometer arm length of our detector, we are talking about measure the length difference of 1,000th of the nuclear size. So that's why in like 80s or 90s, more than 50% of best scientists in the world believe that cannot be done, but it's done. So that's the miracle. So if you know the waveform from signal processing point of view and Gaussian, if it's assumed Gaussian noise, matched filtering is the optimal detection method. What you do is that you actually take the waveform, for different mass pairs and spins, say spin of the black hole and mass of the individual, say black hole neutron stars, you actually correlate the waveform to the data, weighted by noise. It's as simple as that. So the best way is actually to do it usually is to do Fourier transform, because you have this analog and scaling. But however, LIGO science is actually limited by computing power. Why? Because we are searching through from, say, mass of one solar mass to about hundreds of them and different spins. And we want to make sure we retrieve at least 97% of the optimal SNR. And for instance, for advanced LIGO, we need more than 1 million templates, this waveform, to do that match filtering. And it's actually, we cannot do a lot, actually. So that limit, with the limited computing power, we cannot do more than we wanted to. For instance, right now we only can only search for if the spin are parallel to each other. We cannot do if they're not, because that will cause orbit precession, everything. We don't have enough computing power to do it online. Offline, you can do it slowly, that's fine. But what I'm going to emphasize today is online detection in real time with minimum low latency. So here's the schedule of the science run. As you know, the first science run was actually only reached about 200 million light years. That's the first one starting late 2015. Actually, just 2 weeks before we really officially started, we could have the first detection. That's the first discovery of two black holes, about 30 and 35 solar masses, just collide, merge into each other within 1.1 second, and we got it. And then second science run started late 2016 here, and it lasts into the mid 2017. From these two science runs, we have 7 announced ones. those with significant detection, 7 of them, including the first time we detect gravitational wave and light together. Because gravitational wave is a completely different spectrum from the light, electromagnetic light. This is the first time. And the third science run is scheduled January next year. So we are ultra busy because we need to get ready for it because it's going to be more sensitive. And we are supposed to reach a design sensitivity a few years later, about twice more sensitive, which means you should detect 10 times more. So that means you are going to have a lot of detections. One thing for those people who are interested in analyzing data is that because we need to return to the taxpayer, right? We use taxpayers' money to build Detector. The data, the first science run data is already open. The second one is going to be open as well. So that's how we return to the community. So that's the first detection of the merger of pair of black holes. As I mentioned, this is the chirping signals. So what I show here is the y-axis. That's the frequency of the gravitational wave. X-axis is time. These are the axis power against background. And here is the gravitational wave light on the waveform, detected one. And that's for Hanford site. That's for Livingston. You can see very, very significant detection. I just played the audio here to show if you play the data in audio band, because we detect between 10 to about 2,000 hertz, that's audio band. If you played it in audio, that's what you will hear. I played twice. All right. So because of the discovery last year, 3 people were awarded the Nobel Prize in Physics. One is Ray Weiss from MIT, he's an experimenter, and 2 from Caltech. One is Kip Thorne, he's a theorist and astrophysicist, and Barry Barish, who is actually the director who managed it. For the decisive contribution to the LIGO detector and the observation of gravitational waves. So as I mentioned, last year, August 17th, for the first time, we actually detect the gravitational waves from merger of 2 neutron stars. So those are the stars that made up mostly neutrons. Like the whole sun can be packed into the size of our CBD of Perth. Basically really, really dense, right? And here it's just a little summary for the discovery.
For the first time, astronomers have detected a single cosmic cataclysm in both gravitational waves, ripples in space-time itself, and electromagnetic waves, what we typically call light. This hugely collaborative effort includes the LIGO and Virgo gravitational wave observatories, along with a multitude of telescopes in space and on Earth that together collectively monitor the full spectrum of light. The spectacular event was produced by the collision and merger of 2 neutron stars. These objects are the burnt-out remains of giant stars that have exploded as supernovae. They leave behind cores of exotic matter composed primarily of neutrons crushed together under the intense pull of gravity. More mass than our sun is compressed into a sphere that is about the size of a city. Astronomers have long known that neutron stars are found in pairs, orbiting one another. The theory of relativity predicts that the motions of these incredibly massive objects should generate gravitational waves. These waves would drain energy from the orbiting bodies, causing them to slowly spiral together and eventually collide with each other in a spectacular explosion. On August 17, 2017, the gravitational wave chirp was recorded by the National Science Foundation-funded LIGO observatories, and less than 2 seconds later, a short burst of gamma rays, a high-energy form of light, was detected by NASA's Fermi telescope. Researchers quickly realized these 2 fundamentally different types of waves could have come from a single neutron-star merger. If so, it was critical to identify exactly where this had taken place in the sky, and if the explosion could be seen by other telescopes. The Fermi data indicated the burst came somewhere from a patch of sky covering about 1,200 square degrees, an area equivalent to 6,000 kilometers. Adding information from an independent gamma ray detection from the integral satellite, the search area was further reduced. The LIGO observatories placed the source somewhere in long, narrow strips of the sky, one of which overlapped with a target patch. The Virgo Gravitational Wave Observatory in Italy, working in conjunction with LIGO, should easily have been able to detect a signal of this strength, but saw almost nothing. This was an important piece of the puzzle, since any gravitational wave observatory has a small number of blind spots where it cannot detect an incoming signal. Restricting the source location to Virgo's blind spots further narrowed the search area down to approximately 28 square degrees, or 140 full moons. Around 50 candidate galaxies were identified in this area for follow-up observations using optical telescopes. Less than 11 hours after the first detections, astronomers using the Carnegie Sports Telescope identified a previously unseen blip of light in the outer reaches of the galaxy named NGC 4993. Several independent confirmations were reported from other telescopes within the next hour. The first ever optical counterpart to a gravitational wave event had been found. Knowing exactly where to look, astronomers began an unprecedented campaign of follow-up observations using more than 70 telescopes around the world and in space. During the course of the next 2 weeks, the neutron-star merger was detected across the entire electromagnetic spectrum. The gravitational wave data have, for the first time, provided a direct measurement of the masses and orbits of the neutron-star pair before the collision and merger. The data also enabled ongoing follow-up observations across the electromagnetic spectrum, characterizing the explosion and revealing how such unimaginable events had played a formative role in shaping the world around us. These results, for the first time, confirm that neutron star mergers create precious elements like gold and platinum, as well as a host of other heavy elements all across the periodic table. Explosions like these, through our cosmic history, have seeded the universe with the materials that later would form new stars, new planets, and beings like ourselves who look up and wonder.
So at the UWA, our group is running one of the 4 online pipelines trying to detect gravitational waves from binary coalescence as soon as possible. One of the main reasons is that we want to give early warnings of gravitational waves so that once there's an event, we will ask the optical telescope saying, go and look for that part of sky. And why is it so urgent? From the theory, this is one of the figure from our paper is that, so you have 2 neutron star merger. Around the merger, within about 1 second of the merger moment, you have gamma rays, you can have optical flash, you can have X-rays, you could have this so-called fast radio burst, anything. However, for this detection, we only have gamma ray by chance, right? This time we see gamma ray this time, but most of detection at this time is here. We miss this bit. And this bit contains all the best astrophysics here. And we want to catch this moment. Therefore, because this is only lasts for instance, theories at 2 seconds. So it's best we detect it here and give warnings for telescope to get it. If you catch it here, it's also good because even though the signal is fading away, you can still catch the high signal to noise ratio part. So our goal is to catch this bit. To do that, you need to be fast. And you get the sky, not just detection, also sky localizations. So one solution from our team is to design the so-called low latency filtering. Remember the optimal detection method is matched filtering, right? Do correlation, usually we do Fourier transform. But if you do Fourier transform, you have to accumulate data, and that introduces a delay. So what we did is that we actually designed something using so-called IIR filter. We actually have minimum delay, just 1 times that delay. In terms of theory, what we read is because that's the waveform, and we use different damped truncated sinusoid to approximate the waveform at different frequencies, then add them together. So that's the physics behind it. But what we really did is an so-called IR filter. If you are from engineering, you'll see it's called impulse response filter. So for each data points come in, all we need to do is to linearly recombine with the last output. And so the main work is at design the coefficient of A and B here. And we have a series of papers and theses on it. Basically, Y is going to become the signal to noise ratio at each time step. And that's what we have done. And the other thing is because we should have this kind of filter, a few hundred of them for each template. Therefore, they are so in parallel. It's almost embarrassingly parallel, except at the end you have to add them together. That does introduce a little bit delay in terms of high performance on computing. What we found is that for each template, we actually need small number of filters, and we found the computing actually requirement is quite scale similar to Fourier transform, and that's one of the figures to show it. And the second solution we have, once we design this on low latency filter, that means we give out. If there's a signal noise ratio is available, we'll give out within one time step in principle, so it's 0 latency. Second thing we did is use graphic processing unit to accelerate it. That we also have paper here. We actually optimize it at the hardware level. That means you play with registers, local memories, and global memories. We play with the blocks and warps and threads. That's what we did. And we have a pipeline that has been running for the past few years, even though other pipelines are running even longer, but we are one of the 4 right now online doing the low latency gravitational wave searches. And this is how the pipeline look like. The delay of the data packaging, that's not our problem. That's, detector have come to the computer. The data has to come to the computer. That should be able to be less than 4 seconds. At this time it's 10. But then we do whitening, that's 1 second. We do our filtering, we make it 1 second. It could be, millisecond, but what's the point, right? We just put 1 second. And we actually do detection and localization at the same time. We do all-sky search because we can afford it. We have GPU to help us. Then we send it to database, and you can see the entire pipeline can yield the event trigger within 10 seconds. At this time, for the last run, it's all about 30 seconds. But as you see from the astrophysics point of view, every second matters. Other pipeline actually use external localization. That means they detect it first without localizing it, and then put it in the database, and another program come in and localize it. That actually causes a little bit of delay. And here are some data which I should not be showing you, but anyway, that's what we have, the signal to noise ratio, the all-sky map. That's a real true location, which is our localization. So we get this on position really well. So we are going to participate in the 3rd science run in January. We hope to have some discoveries. So we really need supercomputing. That's really important because we need to generate and update those coefficients that we use CPUs at this time by doing GPU acceleration. We need to do a lot of testing on simulated data because the pipeline is just dirty. You have to do lots of tests to make sure it's stable, you're good against the glitches. We need both GPU and CPU computing power, and so far we have received substantial support from Pulsar. Pulsar has been supporting us since the first day I arrived on campus. At that time it was IVAC. And we got it from Swinburne Supercomputing Center, it's called also STAR. And we actually use a lot Caltech LIGO computing cluster. We have dedicated node of GPU clusters for the run. And we also have UW Faculty of Science computing cluster also support us for some nodes. And we are, of course, doing a lot of astrophysics there. The one we check mark is basically what we are doing. But one thing we are really doing relevant to this meeting is that now we are starting to do machine learning because data, we have a lot of data. We start to have signals, and we sort of know what kind of signal to look for. Can you use machine learning to dig out less significant events? So that's one thing we are doing. In terms of future, we are going to have space detector. That's called LISA. That's a European ESA and a US collaboration. It's supposed to be launched in 2034. It already passed the phase that basically it's more or less funded if nothing bad happens. So we are going to detect lower frequency things in space with LISA. And for pulsar timing, we're detecting even lower at nanohertz gravitational waves. Anyway, so in summary, supercomputing power is important for gravitational wave science. And we really want to capture the electromagnetic flashes right at the binary merger. So that means we need to be fast, online. That's give you more computing demand on computing powers. We also, the solution from our team is that we have the pipeline with the GPU acceleration. We have designed extremely low latency IR filters, and we also do detection and localization at the same time. That's different from the other pipeline because they will have more delays by doing external localization. And we think we should be expecting more discoveries and surprises soon. Thank you.